Okay, for today, we're going to discuss the principal stresses and maximum in-plane shear stresses. What we did last time, we had a point in a beam like this, and we found the stresses at that point, and we created a stress element for that point. Oh, I think I forgot the papers. Okay, anyway. So we're doing a lot of calculations today. Okay, from what we did last time, for that point, we calculated the internal force diagram, and based on this, we calculated the stress, like the stresses, and we presented it using the stress element like this. And we learned last time how to rotate that element in case the cracks will be inclined. But the thing is, last time when I gave you, I just gave you a certain angle and I told you to rotate the element about, which I gave you basically those three equations. And those three equations are general equations that are valid through for any angle. But most of the time, we are interested in the angle that will give me the maximum normal stresses and the maximum shear stresses. And sometimes we might be interested in all the angles. That's for stress analysis. People in the mechanical engineering and also civil might be interested in the most of the angles or all the angles. But most of the practices, we are only interested in the maximum or the angle that will bring us the maximum stresses. So before going through this, I want to highlight something, which is, again, if you have a stress element like this, and I'm asking you what is the stresses on that plane, which is same as for that point, I'm having a plane like this, and I'm asking you what is the stresses that's going to come out of that plane. So what you're going to do, nothing new now, you're just going to take this plane or this element, okay, and for that plane, just create the stress element about, which is something like this. And what you want to do, the stress that's going to come out of that element going to be stress n. And what is that stress n rotated about? I mean, what angle? It will be this angle with the x. Okay? Nothing new. Something I want to highlight here, which is for that element that you rotated, the other plane, which is going to be a stress t, it's going to have this angle, which is 90 times theta. And we agreed on that last time. But I want you to notice that this plane and this plane, what is the relation between them? They're perpendicular, or in different words, we call it orthogonal planes. Okay? So for our element, we do have orthogonal planes. For example, if I didn't rotate it, I do have x and y. If I rotated, I have n and t. Tell me, you have a question?
You said 90 times theta?
90 plus theta, because the difference between two coordinates, for example, n and t here, it's 90. And for x and y, it's also 90. So if I assume that theta is 30, so the one that will continue, it's going to be 60 here. And then if you know that this is 90 and you already have 60 here, so this is going to be 30. So it's 30 and 30. And to get this angle from here to here, you go 90 plus 30. Okay? So we do have orthogonal planes here, or perpendicular planes. And the thing is, I don't want you to be confused with the naming. I named here x and y, which is the conventional naming. When I rotated it, I named it n and t. But you can name it anything. You can name it u and v. You can name it, for example, anything, like Alex and Jack, for example. Anything. So this is not the rotation thing is not fixed. So when I wrote here sigma n, I didn't mean n to be fixed. No, I mean anything that you're going to name it n. I just wanted to make that clear so that this theta you will understand that it's valid for any rotation. Okay? For plane 2, you're going to do the same thing. You're going to draw an element that's rotated about this, and you're going to draw a stress that comes out of that element. I'm going to call it n again. And you want to find the theta from the x. Because if you remember how we derived this sigma n equation, we agreed that this theta should start from the x. And it's going to be positive if it's counterclockwise, and negative it's going to be clockwise. So if we rotated it that way, that is positive. If we rotate it clockwise, that's when it's going to be negative. So nothing new so far. What I said right now, you already heard it before. Okay, what is new? So the new is we want to find the angle or the orientation of the element of maximum and minimum stresses. And from calculus, or if you're following up in this class, if I want to find the maximum of a function, what should I do to that function? Before equaling it to 0, what should I do? That's correct. So now what I want to do, I will have this function, and you don't need to write anything. Most of today's lecture are going to be equation, and I have it written here. So for this sigma n function, I'm taking the derivative of the stress n with respect to the theta. So I'm basically taking the derivative of that theta. And if I went through here, I'm gonna find that you can go through it at home, but eventually you're gonna end up with tan 2 theta is equal to tau over sigma x minus sigma y over 2. What does that mean? That means if I want to find the angle or the angles, because when you take a derivative and equal it to 0, you're finding the maximum and the minimum. So to get the angle that will give me the stresses at its like maximum and minimum, you need to take a tan 2 theta or tan inverse of tau over sigma x minus sigma y over 2. This equation will give me the theta, and using this theta, if I substitute it here in the sigma n equation, I'm getting the maximum stresses. Is that clear? I want you to notice something. When I derived this equation and had this equation equal to 0, do you see any relation between the tau nt and this equation? Let me cancel the 2 with the 2, because the whole equation equal to 0, so the 2 gonna cancel. What do you see? This equation and that equation. They are the same, which tells you something. That when, I mean, like they equaled each other for different purposes. The first purpose that I had this equation derived, and I took the derivative of this equation equal to 0 to find the theta that will give me the maximum stresses. But what will happen if I took this equation for the tau and equal it to 0, which in different words, I set the tau equal to 0. What I'm doing actually, I'm finding the theta that will cause the shear equal to 0, which what I indirectly did here. I equaled this equation to 0 to find, for example, the theta will give me the maximum stresses, which in conclusion, what I want to say, at the planes where you have maximum stresses, the shear is equal to 0. Do you all agree with me? Okay, this is the first conclusion. Second conclusion, if you remember from, I think, calculus or even high school, the unit circle, if I want to take that, for example, this is all, which is mean all the quadrants are sine, cosine, tan, they are positive. Here is sine, only positive. Tan is positive. And then all students take C, which is the cosine is positive. If I have a tan theta here equal to some value in that circle, it's gonna also be equal to another value that is also in the tan region. This is what you did in high school. This is not something new. So what I'm proposing here is, for this tan theta, I do have 2 roots. Which is, for example, if you want to try this in your calculator, you can say tan 30 is equal to, let's say, tan 45. tangent of 45, it's equal to 1. But if you say tan 45 plus 180, it's also going to equal to 1, which tells you that for this answer, I have two roots, which means I have two angles that will make this equation correct. I have two angles will give me this equation. Okay? I'm going to call these two angles theta, 2 theta p1 and 2 theta p2, because I'm solving here for 2 theta. Okay? Okay. Now, let's agree on something, which is if I took any of this 2 theta and put it here, one of the 2 theta will give me the maximum, and the other 2 theta will give me minimum. So 2 theta p1 will give me maximum, 2 theta p2 will give me minimum, or the opposite, or the vice versa. We're going to figure this out later. But let me draw the triangle that will make this equation valid. In different words, if I have tan 2 theta here, p, equal to tau over this thing, which is opposite over adjacent, what I'm proposing here is this triangle, which is here 2 theta p. I'm going to call it 1. And this guy is going to be tau xy. And the adjacent is going to be sigma x minus sigma y over 2. Do you see it? That for one root in the equation. But for the other root, what I'm going to do, because tan is also going to give me the same answer in the third quadrant from the ASTC, if you remember it from high school. You remember it? All students take calculus? Okay. And then I do have this 2 theta p2, and now I do have tau xy, but I'm going to call it negative because tau is down, and the y-axis was down. And this point, which is here, I'm going to say sigma s, sigma y over 2, and it's negative. So I created two triangles here. Why I did this? Because I'm going to later use it to derive a general equation that will give me the sigma p1 and sigma p2 right away. Tell me.
Does 2 theta p2 extend from the x-axis, or does it extend from the hypotenuse of the first triangle?
That's my bad. It should start from the x-axis. Okay? Everything starts from the x-axis. Okay? So, bless you. Let's discuss some notes here. So for every slide, there will be a lot of notes so that I'll make sure that you didn't lose me. First thing, that the planes free of shear stress, that's where I do have the maximum normal stresses. And this is what we call principal planes. So the planes that will have the maximum stresses, they are called principal planes. And of course, they're going to be orthogonal. Okay? Why they're orthogonal? We agreed here from the beginning that two orthogonal planes, they are 90 degrees away from each other, right? But here we are talking about theta. Here we are talking about 2 theta. So 2 theta, they're gonna be 180 degree away from each other. So if the 2 theta is 180 degree away from each other, so the theta will be how far from each other? 90. If 2 theta is 180, so 1 theta is 90. Do you all see it? Which makes the stress, let's say maximum, and the stress minimum, they are on the same they're on the same stress element, but they are orthogonal to each other. And for that plane, that they are the principal planes that we have the maximum normal stress on, we call those stresses principal stresses, and we symbol them with P. So instead of saying sigma max and sigma minimum, what I'm going to say sigma P1 and sigma P2. Which one is max, which one is minimum? They're gonna interchange. Okay. What I said here, maximum is P1 and minimum P2, but they might change. But let's now fix this that, okay, maximum gonna be P1 and minimum gonna be P2 for this moment. Okay. Now we found the theta P. And this is not new. If once I got 2 theta P, I'm gonna divide it by 2 to get the theta P. If theta P is positive, that means it is counterclockwise from x. If theta P is negative, that is clockwise. This is we did before when we spoke about the theta in general. Same rules apply here. So when you find the theta P1 or sigma P1 and sigma P2, this is gonna be your theta as if I got an angle here, negative angle. So if I got negative angle, that means the element is gonna rotate clockwise. Okay? Did I lose anyone? Okay. Here comes another question. Okay, when I rotated theta P, is this plane gonna be sigma P1 or it's gonna be sigma P2? How I'm going to figure out this? Going back to the triangle that we created, if I do have the sigma x minus sigma 2 over 2, if this one is positive, which is what you see here, the theta P that you got, it will take you from the x to sigma P1. So this point is sigma P1. But if in the equation that the sigma x minus sigma y over 2 was negative like what you see here, the angle that you got gonna take you to here. And this point is gonna be sigma P2. Is that clear? So to figure out this, you need to substitute in the equation that will be given in the question, which is sigma x minus sigma y over 2. Is it positive or negative? If it's positive, that means you are here. If you are here, then the sigma gonna take, or the theta gonna take you to sigma P1. So if I wanna apply this in this question, if I do have sigma x minus sigma y over 2, and if this was greater than 0, then the theta took me to P1. Same thing here. If you substituted in sigma x, sigma y over 2, and you got less than 0, then the theta takes you to stress sigma P2. Is that clear? Another thing that I need to highlight here, that the angle of principal stresses, we call it principal angles. That's why we symbol them with P, sigma P, because we're going to have another angle that I'm going to explain in a moment. And here, this is what I said before, that sigma P, if it's positive, that means it's rotated counterclockwise. I want to take back something. I said the sigma P1 and sigma P2 might interchange, which one is maximum, which was minimum. No, sigma max, so the maximum gonna be sigma P1 and the minimum gonna be sigma P2. And we're gonna go through this in a moment. Okay. The reason why I drew these two triangles in a moment, what I want to do, instead of getting the theta, the 2 theta, and go back to the sigma n equation here, and substitute with the theta, and get, for example, sigma P1 and sigma P2, why can't I remove the cosine 2 theta? Because I know that this triangle with those angles gonna give me the maximum stresses or the maximum angles. Why don't I find the cosine of 2 theta P1, for example, which gonna be the adjacent over the hypotenuse, and the hypotenuse is gonna be tau xy square plus this guy square under the root, that's the hypotenuse. So if I found the cosine 2 theta P1, which is this over that, and sine 2 theta P1, which is this over the hypotenuse, and basically substitute them in the sigma n equation. Again, what I did, as if I have the numbers, and I have the theta here. I got a value for theta. If I have a value for theta substituted in this equation, I'm going to get the maximum stress. But now if I want to generalize this and I want to symbolically solve this equation, I'm going to remove the 2 theta p and the sine 2 theta and put this two equation. The reason why I want to get rid of the angle in the equation, so that I will have, if I substituted this, I'm going to get sigma p1 is equal to this, with no angle calculation or with nothing. Okay? But this sigma p1 is for 2 theta p1. But I told you that the tan or the theta here that will give me this adjacent or the opposite over adjacent, I do have two roots. So I do have two angles that will verify this triangle. So I do have another equation here, but instead of taking 2 theta p1 and 2 theta p2, instead of taking 2 theta p1, I took 2 theta p2. And now I'm working with this triangle. So some might see that, okay, you said cosine 2 theta p2, and the 2 theta p2 is here. Why did you take the adjacent over hypotenuse, although you're talking about this angle? But I want to remind you something, that cosine 30 is equal to root 3 over 2, right? And if I added 130, I have 210. And cosine 210 is the same value but negative. That's why it makes sense that if I took this theta, I'm also going to get this equation. So cosine 180 plus 2 theta is equal to cosine of this theta, which is the same at the beginning. A lot of math, but this is like very simple calculus or very simple math. Do you all see it? And again, if I substituted those in this equation, now I'm getting the sigma p2. And sigma p2, it's different from sigma p1, that one of them, if you look, the first term is subtracted from the second term. So added up and subtracted at the bottom. So if I want to generalize this as a summary here, for principal stresses, I do have sigma p1 and sigma p2. I do have both equations, and if I want to put them in one equation, I have the first term plus or minus the second term. Is that clear to everyone? For the principal angle, though, the tan inverse for this value, you're going to get one angle. For explanation purposes, I showed you that we have two angles. But when you calculate it, I only want you to calculate the first root, or the root that will come out from the calculator for this angle. For example, tan inverse 3 over 2, you're going to get some angle, and this will be your theta p. I don't need to see the second angle. The second root is just for explanation purposes, just to convince you where the sigma p2 come from, or to show you that I do have orthogonal stresses at the maximum element, or that the principal element. Is that clear for everyone? Any questions?
Yeah, so you would. So if you're asking like this on a homework or.
Yeah, you're gonna see. We're gonna have a example at the end.
No, yes, but you're just asking for one.
Yeah,
basically.
one angle, one angle. The same as at the beginning here last time, when you wanted to find sigma n, you only took this theta. And also last time, if you wanted to do the sigma t, you take this theta plus 90. But today, we're going to cancel this equation, and we're going to come up with equation that we don't need an angle for. So eventually, we only need to do one angle. We don't need to do the 90 plus. That's the whole purposes. OK, what we did now was for the normal stresses. Same thing for the shear. So again, I do have the shear equation. And if I want to find the maximum shear or the angle that will give you the maximum shear, what should I do? Take a derivative again. And if you took a derivative, you're going to find that the tan 2 theta, but I'm going to call it S here. And the reason why I call it S is because that's the theta will give me the maximum shear. I have this over this. And to remind you that the tan 2 theta p was this over this. What is the relation between both? Correct. They are a negative reciprocal of each other. And what does that mean? That means, for example, if I do have this famous triangle, which is 3, 4, 5. And if I want to find this theta is 4 over 3, right? Which gave me the theta. But what if I wanted to find the theta, let me call it alpha now, 3 over 4, which is the relation between both of them. They are reciprocal of each other. This triangle now, or this alpha, is going to be here, because you basically took this 3 over 4. The point that I'm trying to make here, that the theta and the alpha, they both make 90 degrees with each other. So one of them is 90 minus the other. Do you see it? But that in the 2 theta form. 2 theta p, for example, if I want to find 2 theta s, I'm going to say 90 minus 2 theta p. But that's in terms of 2 theta. But what if I wanted to find for the theta s? That's now I'm dividing all equation by 2 to get rid of this 2. To get rid of this 2, get rid of this 2, and I'm dividing this by 2. So what I'm proposing here, that the only theta s is minus 45 minus theta p. Is that clear to everyone? Okay, a lot of concepts in this lecture. This is important just to prepare you guys to understand the Mohr circle, which we're going to discuss next lecture. Okay? So now, as we said before, that the tan 2 theta here, this will give us 2 roots. Now, this should be easy for you now. 2 theta s1 and 2 theta s2. Okay? But when we solve, we only want to find one. But the reason why I'm just showing both, because when I derive, now this will be my triangle. And this will be your theta. Okay? The reason why is this is your theta, S1, is when I say this term, which is now that term, sigma x minus sigma y over 2 over tau xy, that's your tan. That's why this is my triangle now. Okay? Which tells you now that this angle is from the plane element to the shear. It's not from x anymore. Okay? Any questions? Tell me.
In general, when working on these equations, would you rather us work in degrees or radians?
That's a good question. I think degrees will be better. Any more questions? Tell me. Okay. Last part, what I said, I don't have x and y anymore. Okay? This is not an xy diagram. When we talk about xy diagram, this theta gonna be from the x. But now when we talk about the stress, the normal stress and shear stress diagram, which is later, I'm just preparing you again for the Mohr circle. Mohr circle is not gonna be on xy, it's gonna be on normal stress and tau. So from this line to the tau, this is your theta s. But in 5 minutes, when we talk about x and y, when we convert coordinates now, or the axes now from x, y, this angle is going to be still from the x. But what I'm showing here, that there is no x and y here. It is sigma and tau. And again, the reason why I showed this triangle, because I want to come up with a conclusion where if I find the sine 2 theta and cosine 2 theta for this triangle, I'm going to get, and substitute, of course, in the tau nt equation, I'm going to get a tau max, which has no angle in it. It is just this term plus this term. You're having the maximum shear stress. But if anyone wants to, of course, get this theta s, substitute in this equation, you're going to get the same thing. Same thing. I'm just giving you an equation that has no angles in it. And again, all the equations that we derived, we're going to use it in the Mohr circle. So all this is preparing you for Mohr circle. It's like one of the challenging topics in this class. And the next slide again, Mohr equation, but instead of working with 2 theta s1, I'm working with 2 theta s2. And I derived that the tau max, same equation, but one of them is positive and the other one is negative. To summarize, a lot of equations I know. When we solve everything gonna be easy. But to summarize, I do have shear stress angles, which is 2 theta S1, 2 theta S2. Having two of them is just for explanation purposes. Only calculate one of them, which is the first rule that you're gonna find out. Okay, what we found that the tau max was equal to positive or negative this term. But positive or negative, it has no physical meaning, like normal stresses. If I have positive normal stress, that means I have tensile stress. If I have negative normal stress, that means I have negative or I have compression stress. But for shear, it is just direction. In different words, last lecture, when we wanted to come out with a tau nt from the first place, we assumed that the tau is going that way. Okay? And when we just did the summation fn and summation ft, we had that the tau nt equal to positive because this direction, for example, was correct. But if you have tau equal to negative, that means the plane that you are working with is no longer having this tau looking that way. That means, for example, you have this plane, and the tau now gonna look that way, which is your assumption at the beginning that the tau looks up is incorrect and you should invert it, which also aligns with the element or the sign convention for the shear. I have one side going up, and where is the other side for the positive sign? It's going down. But this equation doesn't see it. This equation is summing from one side and summing from the other side. This equation doesn't know about the sign convention for the shear. Is that clear to everyone? So what I want to say, okay, now neglect the signs, and when you find tau max, I want you to find the absolute tau max. So forget about the sign and take the shear, maximum shear stress for the element equal to this. So what we did so far, for an element, if I give you the x and y, I'm confident now that you know what stresses to substitute with to get the maximum normal stress, what equation you're gonna substitute with to find the maximum shear stress without giving any angle. But if you want to find angle, I already gave you the tan 2 theta p that will give you the angle for the normal stress, and if you substitute it in the sigma n at the beginning, you're gonna get the maximum normal. And also, if you want to find manually the maximum shear, you're gonna get the theta first, theta s for the shear stress, and you're gonna substitute in the tau nt equation. So you have two ways now to find the maximum stresses. Okay. Lastly, let's find some properties or some shortcuts. If I took the sigma p1 and added it to sigma p2, so this is sigma p1 equation, and this is sigma p2 equation. If I added them to each other, you're gonna find that this term cancels that term. Okay, and here is the important thing to notice. Sigma x plus y here, when you add half sigma x plus y plus half sigma x plus y, you're gonna end up with sigma x plus y. And here's an important conclusion, that for a plane stress, the sum of normal stresses, and these normal stresses are at any two orthogonal planes, like sigma p1 and sigma 2, they are orthogonal. X and y, they are orthogonal. The sum of them are constant and they are independent of the angle, which will make our life easy in the moment. If I took this copy now, and I wanted to go up at the beginning of the lecture, and now instead of substituting in this equation and finding theta plus 90, what I'm proposing here, instead of p1 and p2, let's generalize this by saying n and t. So if I know that the sum of the orthogonal n and t is equal to the sum x and y, now the stress at t is equal to sigma x plus sigma y minus sigma n that you got it from the beginning. And now we can cross that one out, and we can simply use this to find the sigma t. Is that clear? Second property that we need to look at is what will happen when I subtract the principal 1 minus principal 2. So when I subtract them, you're going to find out that now the first term cancel each other. And I'm going to be left with this root and that root. And when I add them, I have sigma p1 minus sigma p2 is equal to 2, that's square root. And if you remember, that square root was tau max, which we're going to end up with some with an important equation here, which is tau max now is equal to p1 minus p2 over 2. Okay? This is one of the shortcuts that you can use. Finally, before solving our example, p1, sigma p1 was equal to sigma x plus sigma y over 2 plus that term. So let's create a new symbol here by saying sigma x plus sigma y over 2, that is sigma average. So that's the average stress. And the second term was tau max. Okay? So what I'm proposing here, the new equation for P1 is equal to sigma average plus tau max. And therefore, sigma P2 is going to be sigma average minus tau max. And we're going to use this now in the example. So what is the example? The example is going to be given something like this. It's going to tell you, when I break this element didn't break in x and y, as you can see here. I don't know if it's clear or no. But when this element broke, it broke with an angle, as you can see here. Do you all see it? And I'm going to ask you now, okay, what is that angle that it broke at? Because if it's broken angle didn't break at x and y, then there is another stress element that has normal stresses that is greater than the normal x and y stresses. So in this case, it's going to give you the configuration of the test or the stresses that are applied to that element. And first thing that I need you to do, I want you to just write it down. What is the x, what is the y, what is the tau x and y. From reading this graph, you're going to find that sigma x is 11 ksi. Sigma y, negative 9 ksi. What about the tau? Minus negative 7 ksi. Okay, before just looking at the problem, just write these out. And then I'll be asking you, determine the principal stresses and the maximum in-plane shear stresses acting in the point. The shear stresses that I mentioned, the tau max is equal to square root. This is plane stress. This is in-plane stress. I didn't show you a cube or anything. I was just working on 2D. Because next lecture, we're going to extend these concepts to 3D. But since it's a 2D, so that's why we call it in-plane shear stress. Okay. Now, what I want to do, I want to find the principal stresses. So for principal stresses, I'm going to use this equation, which is P1 is equal to sigma average plus tau max for sigma P1. For sigma P2, I'm going to say sigma average minus tau max. And I'm using this equation, but you can use like any form that you want. Okay, now I want to find the average, the sigma average. What was the sigma average? It was sigma x plus sigma y over 2, which is the average stresses. You're going to find that 11 minus 9 over 2, it's going to equal to 1 ksi. Okay? Second thing, I wanted to find tau max. So tau max is equal to square root, common mistake, that you say sigma x plus sigma y. No, it's not sigma x plus sigma y, it is sigma x minus sigma y over 2, and this is square, plus tau xy square. Where I got this equation? It was from the hypotenuse of the triangle that I mentioned before. So hopefully you know everything where it came from, and hopefully everything makes sense now. So if I want to say now, sigma x is going to be 11 minus minus 9, which is plus 9, over 2, this is square, plus tau xy square. If you did this, you're going to get 12.2 KSI. Let me double check that. Yeah, it's 12.2 KSI. Of course, it's positive because I eliminated the negative term. I don't know the sign of the shear yet because I just eliminated at the beginning, and I'm going to show you a method now so that we can know the correct shear stress sign. Okay, now let's just get the absolute maximum shear stress. I'm going to write ABS here, and just basically substitute in the sigma P1 and sigma P2 equation. So I'm going to get the sigma average is 1 plus 12.2 KSI, so that's 13.2 KSI, and now it's in tension. The bottom equation, I have 1 minus 12.2, which is 11.2 KSI. And that's minus KSI and its compression. Now I know for this element, when I loaded it in x and y, I know it's going to break with the stresses, normal stresses, that's equal to 13 in tension and 11 in compression, which is, of course, higher than the x and y. In x and y, you applied in x 11 KSI in tension. However, it broke in 13.2 KSI in tension. So if you designed your element this way, it is unsafe. That's why we discussed this lecture, so that you can design your element or your structure element or your mechanical element in the angle that will cause the maximum stresses. Okay, we figured out the first thing. So the second thing tells you, show these stresses in an appropriate sketch, which is basically what I want to do. I have the xy, and I do have two elements. And the reason why I have two elements, because I do have a theta s and theta p. I do have an angle that will take me to the maximum normal stresses, and do have another angle that will take me to the maximum shear stresses. So let's find those angles, and I will start with tan 2 theta p is equal to, I don't have the paper, so I'm going to copy. 1 minute. Did I lose anyone? All clear? It is very simple, trust me. So I'm going to calculate this, and then that guy. Okay? So tau xy, it is negative 7. Sigma x minus sigma y over 2, which was that guy. When I calculated it, it was 10, which is 11 plus 9, which is 20 over 2, that's 10. So I'm going to say negative 7 over 10. Now, if you find the tan inverse for the 7 over 10, you're going to find that is equal to negative 34.99 degrees. So the angle now is negative, which means if I divide it over 2, 1 minute, let's get this one over 2, you're going to get theta p is equal to negative 17.49. Since it's negative, that means we are rotating clockwise. Right or wrong? Okay. So now I know from the x-axis here, if I rotated with an angle theta p, which is equal to 17.49, I'm going to the principal stress element. And I'm going to write P here to indicate that this element now is the principal element, principal stress element. Okay, two ways to get the theta s. Either saying, okay, tan inverse, okay, I know that the bottom here is 7, and at the top is negative 10 now, you can say 2 theta s, which is tan inverse this. So I'm substituting in the stress, like the tan theta s equation. I found it's 55. If you want to find theta s now, divide this by 2. It is 27.5. This is one way to do it. And in this lecture, I taught you a lot of ways. Other way, I can say, since I know that theta p makes theta p and theta s, they are 45 degrees from each other, and the 2 theta and the 2 theta are 90 degrees from each other, so I'm going to work with the theta. So if I said 45 minus 17.49, I'm going to get 27.51 as well. So another way, you can say theta s is equal to 45 minus 17.49, and you're going to get 27.51, because both of them make 45 degrees. Are you convinced? Anyone? Okay.
How do we know it's 45 degrees?
Okay, from here, since I told you that the tan 2 theta p is a negative reciprocal of the tan theta s, now I proved you that the both of them, that 2 theta s and 2 theta p makes 90 degrees of each other. If I want to find now the theta s, I'm going to eliminate the 2 or divide the whole equation by 2. That's why I found it 45 degrees from each other. Okay. Now I knew the theta s. So I'm going to go up here, because both of them makes 45 degrees, so the theta s continues the whole 45 degrees here. Okay? Now, I know that this element now gonna be the S element, which is the shear element. And I know that the maximum shear is equal to 12.2. But the question gonna be, is this 12.2 positive or negative? I told you at the beginning we eliminated from the tau max absolute equation, but if you want to figure it out, you found the theta s that will give you the maximum shear, right? Go substitute in the tau nt equation, which is the general equation here. And you're going to find, when you substitute, that the tau nt is negative 12.2. Of course, you're going to get 12.2 because tau max was derived from that equation. It was 12.2. But now, if you want to know the sign, substitute with the theta s in the general equation. Okay? There is a lot of method, but this is the method, one of the methods that I like. And then now I know that the shear here is negative. Another question, I didn't continue this here. Another question will be, okay, now I figure out that this is theta p. First of all, will I have a shear stress here or no? I will not have a shear stress. Common mistake. Some people put the principal shear stress. No, I proved to you mathematically there will be no shear stress. Okay, and you also, if you took the angle of theta p, substitute in the tau equation, it will definitely be 0 if you want to double check. Okay? Just give me 2 minutes. For theta p, for p1 and p2, I found them. I found one of them is 13.2 and 11.2. But which one it's going to be here and which one is going to be here? Remember when I told you that if sigma x minus sigma y over 2 was greater than 0, that's when we are in this part of the triangle, which is here theta p1, sigma p1. So if you substitute in this equation, sigma x minus sigma y over 2, and you got positive, and here we got positive 10, which means the theta p that we calculated, it is from x to theta p1, sigma p1. Did I lose anyone? Okay, and sigma p1 here was equal to 13.2, and that's why I drew it in tension, KSI. And the orthogonal or the perpendicular plane here gonna be sigma p2, which is 11.2 in compression, not in tension. KSI. And of course, there is no shear stresses in this element. But what about the shear element? Will I have a normal stress or no? Okay, let's do a very quick side quest here, which is just very quick. How to find the stresses? Anyone from what I explained, just to make me happy. If I want to find the stresses at the plane where I have the maximum shear stress, and the plane of the maximum shear stress has a theta. From what I explained, how can I find the stress at that theta? Anyone? Don't look here. Repeat the question. Okay, for this theta, I have a theta. And for this theta, I know the shear. But I don't know the stresses. How can I find the stresses for that theta? What's that? No, here is not in x and y. X and y is that guy. Here is in, for example, n and t.
I'm saying like to remove the theta.
If I want to remove the theta, we are talking about the maximum minimum. But now, in the shear stresses plane, we don't have maximum minimum. Again, if you have a theta, can you find the stress at that theta or no? How? Yeah, substitute in the equation. So here, here I just took the theta, and instead of substituting the theta, because I want to generalize this, I took the cosine, the theta s, and substituted in the sigma n equation, because that's the only equation that I know with any given theta I can find the stresses. And if you did this, you're gonna find for sigma n that the sigma n was equal to sigma average, which is if I substituted, you're gonna see that these two terms gonna cancel each other. And if they cancel each other, you're going to end up with sigma n is equal to sigma x plus sigma y over 2, and this is sigma average. And if I want to find for now t, and using the quick equation, which is x plus y minus n, you're also going to find sigma x plus sigma y over 1 minus sigma x plus sigma y over 2, which is 1 minus half, is equal to 1. So now sigma n and sigma t, for the plane that you have the maximum shear stress, it's going to be the average. And what was the average? It was 1 KSI. And it was in tension, so I'm going to put here the sigma average, and that will be always possible. That's always the case for the plane that you have maximum shear stress. 1 KSI, 1 KSI, 1 KSI. Is that clear? Any questions? I want you to go back home, look in this lecture again, because we're going to use all these concepts to generate the Moore circle next time. Okay? See you in the session tomorrow.